Why is that a good way to write the solution? It's a multiple of the initial speed. What better be true about this junk? Yeah, it's true. If you stuff in 0 for t, it does go to 0. I'm looking for something a little deeper. Yeah. It better, right? Okay, you can't add 1 plus 3 oranges. Okay? It has to be dimensionless, so it better work out that the units of m divided by k v naught is a time, so that looks like a t over some constant time. Agreed? What would this function look like? So it clearly starts at v naught, and then what would you say the time scale for changes is? What is this function going to look like? Well, for very long times, I get to ignore 1 compared to that term. Eventually, the term proportional to t will dominate, and I'll just look like a 1 over t kind of curve, right? So that's going to look something like out there. And I got to end up here. So I'm going to predict a curve that looks a little bit like that. Suppose instead that I try this technique I'm foisting on you of removing dimensions. Then I might say v, which has units of, for instance, meters per second, is equal to some dimensionless velocity v multiplying v naught. And I might say that t is some dimensionless time multiplying a time constant tau. And if I substitute that in to the original differential equation, dv dt will become d v naught over d tau t tau, which is the same thing as v naught over tau dv dt. So notice, these are the only things that carry the dimensions. If I'm going to have something that has the dimensions of acceleration, that's how I'm going to have to get it. And if I substitute into the equation that we have above, dv dt is equal to minus k over m times v squared. So wiping out the constants as much as I can, I have minus k v naught tau over m v squared. And so I could pick the value of tau as m over k v naught. And look, that's what it had to have been in order to produce a dimensionless fraction in the bottom. So you can get at this either way, either by pulling the dimensions out initially or pulling them out after the fact. V is now 1 over 1 plus t Yes, sir.
So in recitation, when we were going over problem 2,
Yeah.
we did it using d big X, d big T,
Yep.
big V.
Yep.
What's the difference between the problems that makes us use
Yeah.
big V in this one?
Right. So the difference was that we had two drag terms. We had linear one, so we had something like kV, and then we had kappa v squared. So we picked a length scale, and we picked a time scale. Does that necessarily then pick a velocity scale? Yeah, because the scale of velocity is going to have to be in multiples of L over tau. That's the only thing that gives the dimensions. So then in that problem, depending on what your actual initial speed was compared to L over tau, which, by the way, L over tau were determined by making the differential equation as easy as possible based on the values of what? K and kappa. So now I'm forced to say, well, V naught, the initial velocity, might be exactly equal to L over tau, in which case the initial value of the dimensionless velocity would be 1. But it could be bigger or it could be smaller. And so in that problem, I had that extra, if you like, degree of freedom.
Yeah, so I guess my question is why did we not do that here?
We could have.
Okay.
We could have. We have to get the same cluster, although having picked a different L and T, I might have a different multiple there. Okay.